Good morning and good afternoon, everyone. Thank you so much for calling into this webinar. We will get started in another minute or two to give more people a chance to jump into the webinar. As people are jumping into this webinar, do note that the GoToWebinar will have a questions entry. So as we're going through this webinar this morning, do feel free to put in any questions that come to mind as we go through the content. We'll make sure to answer that in the question periods if we have time. And if not, we'll make sure to respond to you via email or give you a call to make sure the concepts that we're presenting in this webinar make sense and everyone's having a good learning opportunity. Again, we'll give it another minute or two before we get started with the webinar this morning. I want to thank everybody for calling in and joining us today or this afternoon or this morning, depending on your location. Okay, so I think we have a fair number of people that jumped onto the webinar. Again, thank you everyone for jumping on to this webinar. My name is Dave Lewis. I'm an engineer here at Bentley Systems. And today I am presenting the Lightning Protection Systems and Shielding Evaluation Methodology. This webinar is meant to be a learning opportunity. So if you are familiar with GoToWebinar or not, there is a place where you can enter in your questions that will allow us to review those questions and provide feedback to you and give a response during this webinar. If we don't get to your question during the webinar, we will make sure to answer that at a later date. So let's go ahead and get started. So the purpose of this webinar is to really provide a basic overview of lightning protection systems and the engineering methodologies for evaluating the protected zones of a lightning protection system. At the end of this presentation, it's really my goal that you'll be able to describe basic concepts of lightning protection, of lightning and the components of a lightning protection system, be able to explain the evaluation methodologies that engineers are using for evaluating the efficacy of their LPS, and be able to perform some lightning protection system shielding calculations yourself and understand the fundamental concepts behind those. As we get into or how we apply that, we're really going to be going through a basic overview of lightning, the components of a lightning protection system, and we'll talk about lightning analysis and what engineers may mean when they talk about a lightning analysis. What we'll focus on in the major portion of this webinar is really the shielding evaluation methodologies, and I'm using plural because there are multiple evaluation methodologies to determine protected versus unprotected zones. And we'll go through a couple case studies to really highlight how engineers can provide these. Before we get into this, or before we go into the basics of lightning, we do have a few poll questions that we'd like to better understand the audience so that we can kind of tune this discussion as we go along. So the first question is, have you attended training for lightning analysis before now? If you can, please respond. Definitely appreciate that. Let us know if you are new to the subject, this is your first time seeing these concepts presented, if you've attended some training, either internal or external, or if you've just simply had some discussions with colleagues, might be at a dangerous level of knowledge or well-equipped to perform these. Definitely appreciate everybody's vote on this. And we have a really good split this morning. So we have about a third of the audience is new to the subject. Similarly, we have some that have attended training in the past, and others, a fair number, the majority, have had some discussions, but not any sort of formal training. That's great to note for us as we go through this. Another one to help us along here is, how familiar are you with the lightning-related standards? And this is just a couple of standards, so these are more biased towards North America. If you're calling in from other parts of the world, you may be familiar with the IEC. But IEEE standard 998, this is related to lightning protection systems for substations. NFPA 780, this is related to general buildings, generic building lightning protection systems. So we have an idea of what we might see from this based off of the previous poll, but we'll go ahead and share the responses here. So I think there's a good mix of knowledge here. So I think most people seem to be new to the subject, might have had some discussions, but haven't practically applied those. So we'll make sure to show how an engineer might actually approach these types of analyses. And there's a number of the audience that are familiar with the NFPA 780. And we have one last poll here, kind of gauging how often you're actually performing these. I think most of the audience will be in this none to 1 to 2, 1 to 5 category, but I'm sure there's some that are some technical experts on this call as well. So appreciate your taking the opportunity to fill in these poll questions. And I think we have a quorum here, so I will go ahead and share the responses. So great. Really appreciate everybody answering these polls. I think we really want to make this a great learning opportunity for everyone. And I want to highlight that we're really doing a basic overview of lightning analysis, lightning protection. There are over 500-page manuals provided by some vendors that really give a more thorough description of all the instances of all the nuances of lightning protection. But we're just going to give a basic overview so that people can visualize how engineers are approaching these types of systems. So let's go ahead and talk about the basics of lightning. When we talk about lightning, it's first we want to be familiar with the different types of lightning. So I think most people can visualize what lightning looks like, but there are different types that we can call or categorize lightning as either positive stroke or a negative stroke. So there's a polarity associated with that. We can actually have a lightning event within a cloud itself or between clouds. What we're really concerned about when an engineering perspective is not going to be these lightning events that are within a cloud or from cloud to cloud. We're primarily going to be concerned about providing protection for these cloud to ground events. So we can see this illustrated here as a typical lightning event. And another one to be familiar with, or another type of lightning event, is the tall structures to cloud, where we can actually incite lightning events because of the elevation or the height of a structure, for instance. But for the most part, we're going to keep things below 60 meters and look at a basic cloud to ground application for this instance as we walk through this workshop or the webinar. Do want to bring up some terms or terminology that you may not have heard before. One of them is ground flash density. So this is a measure of how frequent a lightning stroke or a flash occurs within a given area. As you can see in the panhandle of Florida in North America, we have a significant number of ground flashes in these areas, as well as in Africa. You may not have measured values for this. In North America, we have a pretty robust measurement system. Some other countries have this as well, so that we can actually measure the stroke current or the energy that was associated with a lightning event, as well as where that may be and the time or the instance of when that happened. Other ways to calculate this may be just based off thunderstorm days and how frequent or violent or active those thunderstorms may be in a given area. So there's different approaches, but measure is obviously the best. Another term to be familiar with is the step leader. So as illustrated here, when you think of lightning coming down from the cloud, it kind of makes these jagged paths coming down. And these are referred to as the step leaders. So dependent on the energy or the stroke current of that lightning, that will relate to how large of steps this lightning path may be. And as we make our way down from the cloud to the earth, you'll actually have a step leader, upward leader, coming from the earth, or the structure that may be about to be struck. The slow motion video captures of this often will show you can have one step leader or you can have multiple step leaders. And another term to be familiar with would be our return stroke, so our return stroke current. So we can see the step leaders coming down from the cloud, and then this bright flash occurs. That bright flash is when we have total ionization path from the earth to the cloud. So we have a significant amount of current. That current can be 30 Ka, 100 Ka, 300 Ka. A significant amount of energy can be discharged in this lightning event. And the the magnitude of that first current is referred to as the return stroke current. And again, that can be either a negative stroke or a positive stroke. And that first stroke is really what we are concerned about causing damage on our infrastructure, whether it's a building or a substation or transmission line. Now, when we talk about lightning protection systems, it's good to be familiar with what components are used in that. Air terminals is going to be something for those of you that are familiar with NFPA 780. Here we have an image of a lightning protection system. We can see the conductors running along the edge of our structure. And then we have our air terminals extending above the edge of this wall. And that is meant to intercept any lightning. We also have shield wires, which are very common for transmission lines. For instance, we have a shield wire just above the phase conductors on this transmission line, or we have masts, or again, we could use air terminals. So here we have a bunch of buswork, and above that buswork is our air terminals extending above our equipment to help protect those from any direct strokes. Other parts of the lightning protection system that aren't directly involved in the interception of that lightning event are our down leads. That's going to allow us to pass that current or energy from the lightning event down to Earth. At the Earth, we have our grounding system, and it can be something as simple as a copper loop that goes around our structure, or a full grounding system that we would see at a substation or a transmission tower. And this grounding system, depending on how well it's constructed and how it's interacting with the soil, will allow that energy to disperse from that lightning event. Obviously, we're going to have all of our connections too that are going to be very important to be able to withstand that significant amount of current on that short duration, as well as from a heating perspective, the thermal limits of that material, as well as a physical limits, because as you have a lightning impulse coming through a connection, it's going to have some significant physical or Lorentz forces that are going to try and force that connection apart from any other metallic structures. So the air terminals, shield wires, masts, down leads, grounding system, the connections to them, they all need to be designed properly, connected properly, and maintained in order to have a functional lightning protection system. So you can't have one leg working without the other two. Now with that, we can kind of segue from our basic understanding of lightning and lightning components into lightning analysis. And I think this is something that is often misunderstood when we talk about lightning analysis. It depends on who you ask, but when you talk about lightning, there's a risk assessment. So how likely is there to be lightning in your area, and lightning of sufficient magnitude that's going to affect the facility that you're trying to protect adversely. Next, we can look at shielding. So if there's a lightning event in our area, once we've gone through this risk analysis, where is that lightning going to strike? Is there a zone that we want to protect? Are there zones that we really don't care about and we can allow that lightning to discharge without any sort of interception? And then finally, what happens when that lightning actually hits a structure, whether it be the intended structure, our lightning protection system, or an inadvertent structure? And that would be a lightning transient analysis. So when engineers refer to their lightning analysis, there needs to be a little more granularity on what exactly they're referring to with that. And to go into this with a little more detail, when we refer to a lightning analysis, typically this can be something that's calculated based off guidance from NFPA 780, the IEC 62305, IEEE 998 has guidance as well, but fundamentally they are following the same types of methodology or concepts. We have an area that our structure is located within, and then some distance away from that structure, we can associate that with a possibility that a lightning event within this area can affect our system. So we will calculate a given area associated with our infrastructure that we want to protect, typically based off of the height of that object and some calculation of a distance off of that height. Then we can calculate the ground flash density. And based off of the area that we consume compared to the ground flash density, that gives us a rate of lightning events in our area or within a place that we are trying to protect. These will often consider the cost of damage. So if a non-important structure is hit and easily replaceable, then we may not provide lightning protection systems. If it's something that's critical to operations, so obviously substations are critical infrastructure, as that is going to feed into all sorts of businesses, industrial complexes. Databases are critical infrastructure as they house a lot of our data. The hospitals, these other things that are going to provide very critical services for our infrastructure and personnel, that is going to be a significant factor in your risk assessment. If it's important, we want to protect that even if the risk is low, because the hazards associated with the failure to protect are significant. Next, we'll talk about lightning shielding, and we're going to focus on this as the tail end of our webinar so we can really hone in on shielding methodologies. So shielding analysis is really to determine what areas are going to be struck in a lightning event and what areas may not be. And I will note that lightning is probabilistic in its nature. So we may have a lightning protection system that can provide 99% likelihood of coverage, but there's still a chance that we could have a bypass or some sort of unintended strike. Now, here we see a structure, just a simple illustration of one, and the lightning protection system, you can see the mass extending above that, but there are multiple parts along the edge that we have not protected sufficiently. So that would be a unprotected structure in this instance. And this is where we're going to focus on in our webinar in the second half, so we'll come back to this. Now, the lightning analysis or lightning transient analysis, this tells us what happens when lightning strikes. And as you can imagine, lightning is an impulse. It's not a sinusoidal frequency like our power system. It is going to be a steep rise in current. It could be in the microseconds, a couple microseconds. You can go from 0 to 100 kA. And we need to understand the conductive effects of that, the inductive effects of that, and the capacitive coupling associated with that as well. So we can model such things like a transmission line, see the stroke current propagating down from our shield wire as it goes down to the earth. And this little illustration indicates the ground potential rise that we see, or the Earth's surface potential, as the ground rods around that lattice tower are dispersing that current into the Earth. And what we are concerned about is this peak voltage along all of our components of this lattice tower. If your insulators supporting your phase conductors is not sufficient, you can have this peak current actually exceed that insulator, and you could have a flashover and then have an outage of that line. You can also have a poor grounding system, and instead of this peak current going up and reflecting back down, it can go up and, similar to a wave, start to go down before it bounces back and increases again. So these lightning transient analysis can get very detailed to determine the likely or exactly what's going to happen as the current's propagating through this metallic structure. And this could be applied to critical buildings in order to see if there's going to be a side flash, transmission lines and substations. All these are more critical infrastructure that you can evaluate with higher detail. Now let's get to the focus of this webinar, which is really how engineers are evaluating the efficacy of their lightning protection system, or the shielding evaluation of their lightning protection system. Typically, I guess for those that have attended any sort of external training, you'll typically walk through the more simplified methodologies and then walk into a more complex method. I kind of like to think of it as a take the opposite approach in explaining this, because I think the rolling sphere methodology and the electrogeometric methods really do a good job in explaining the fundamental characteristics of how lightning makes connection with structures. So rolling sphere methodology, some of you I'm sure have heard of this term. This is a electrogeometric method, and as you have your step leaders coming down from the cloud, the distance, the strike distance associated with this is going to be related to the energy or the stroke current of that lightning event. Now you can relate that to a sphere size from your lightning as it comes down. And you can kind of see this illustrated here. This little circle represents the striking distance off of the end of our downward leader, and it's within the upward leader, so you're anticipating the next step will be this strike, and then you have a return stroke current. Now, depending on your standard or what you're looking at, you may have a specific sphere size. So NFPA 780, ordinary structures, it's going to refer to a 45-meter sphere radius, or more critical infrastructure, or things that may have some explosive nature to them, could use a 30-meter radius. Depends on the application, what is most applicable for your site. The 30-meter radius is going to be a more stringent application, and we'll get into that as we talk about IEEE standard 998. So IEEE standard 998 is the standard that discusses in more detail how the rolling sphere methods were developed, the different variants of that rolling sphere methodology, since there are a little bit different electrogeometric methods, but the most common one we'll talk about here. And what we're looking for is to calculate the minimum stroke current that can cause us significant damage. So when we look at this from a substation application, we have our sphere that we are imagining rolling over our system. And as that rolls over the fence line, some of our support structures, or a mass, that these masts are going to provide a zone of protection below them and an area where there's unprotected from lightning above them. So here we can see this rolling sphere can roll, and this piece of equipment may be susceptible to a direct lightning stroke, while this one is protected from that. Now that I mentioned, we're looking for the minimum stroke current, and the reason is the smaller your stroke current is, that correlates to a smaller sphere. And you can imagine if we were to shrink this sphere down to half the size, that sphere would be able to roll over this mast and roll down, roll over this mast and roll down, and now this transformer is no longer protected. If that sphere was of insufficient magnitude, or the return stroke current was insignificant magnitude to cause a outage, we don't have a problem. However, if it is significant enough that it exceeds our insulation levels at our utility substation, we could have an outage at that substation, and could be a critical issue for us as we're trying to maintain power for users in a storm environment. Now, another method that we are going to talk about or be familiar with is the fixed angle method. And this is easy to understand when you think about that rolling sphere. So based off of the height of our masts or our air terminals, we can calculate the fixed angle that we may assume some protection to other components or equipment or a structure. So depending on the height of our mast for a substation application using IEEE standard 998, your fixed angle may be a 30-degree angle off of the mast, or a 45-degree angle, depending on how high this mast is relative to the buswork or the transformer that you're trying to protect. A similar concept for NFPA 780, a little bit different angles, but if you have a structure that maybe has a roof line difference of 25 feet from one roof to another, you may be able to use a 60-degree angle of protection, indicating that air terminals on the edge of your upper roof line may provide some extended protection to the roof line or the lower roof line below. And again, that angle is going to vary based off of the relative height difference from your air terminals or masts to whatever you're trying to protect. And if you think about this, we're really going back. If you look at the rolling sphere, which has this little curve, if the sphere is large enough, that rolling curve starts to look like a straight angle. So it makes it nice and easy to understand the relationship or how these fixed angle methods come about. Another methodology is more of a prescriptive approach. So NFPA 780 is really a guide for how you install these systems and is meant to install them properly so that you have a protected system. And this is going to describe how frequently you space these air terminals, represented with the blue lines, the connections to your conductors to down leads, how frequently those need to be done to the earth connection or ground connection, as well as any sort of internal connections across the roof line if it's a significantly large roof. You may need to make connections every 50 feet or run a cross lead every 150 feet, depending on your structure geometry. There's also another methodology described in the IEC, which is the mesh methodology as well. And as you can imagine, both of these are more prescriptive. They are not telling you that you're not giving an analysis that you've met you've created this lightning protection zone. However, properly following these methodologies, you should create that. However, challenges is that you need to also commonly prove that your design is actually meeting your intended goals. So that's where we're going to use the fixed angle methodologies or the rolling sphere method in order to show our clients or be able to prove to our leadership that we have a protected system against lightning. So let's go ahead and apply the rolling sphere methodology. I think the rolling sphere methodology tends to be one of the most commonly utilized in industry. And I think it's best to do this first by going into the source document, which is IEEE standard 998. This is the one that helps us calculate how we get a sphere size or how we get calculate that return stroke current that's going to cause damage to our structures. So we have a few calculations we need to do. So this ZS calculation, this is the surge impedance that a lightning stroke current will see when it hits our structure. And this is calculated by multiplying 60 times the square root of the natural log of 2h over RC, natural log 2h over R. The R, or the H value, I guess, is the height of whatever conductors you're trying to protect. Those phase conductors of a substation is what this calculation methodology is considering. But same concepts would apply to another type of structure, such as a structure that is housing explosive materials. You can use the same type of calculation to make sure that you have a correct protection zone. Your R value is the conductor radius. That's pretty understandable. But this corona radius, this RC value, is actually another series of equations that you can look up in the annex of IEEE 998. So part of that will have a figure lookup to determine the corona radius, or you can create some calculations in Excel or use the software in order to calculate that. But this would be kind of our first step in our calculation methodology, is determining that surge impedance. Next, we can use that surge impedance to calculate the minimum stroke current that exceeds our BIL. So this IS will equal BIL, which could be described as the basic impulse insulation level. You may see this described as the basic impulse level, basic insulation level. Really, we're all referring to the same thing. It's the peak voltage that your equipment or your insulation equipment is able to withstand without a flashover. Another term you may have heard of is the critical flashover. That's really a value associated with that. At a certain peak voltage, there's a 50% chance that you could have a flashover, and those are interrelated to each other. And then now that we have the calculation for the minimum stroke current, we can take that value and now put this into our sphere radius or our striking distance. So we have this S will equal 8 times the K coefficient. This is related to what type of equipment you're using or lightning protection system you're using to protect your system, whether that's a lightning mast or a shield wire. They can have a mast would have a coefficient of 1.2, a wire would have a coefficient of 1, and then that is multiplied times your minimum stroke current to the 0.65. So if we do this calculation, let's say we have a 115 kV switch yard that has a 400 kV VIL design. And based off of our calculations for ZS, we determined a surge impedance of 450 ohms. So that will feed into our minimum stroke current, which would be approximately 2.5 Ka in this instance, which then feeds into our minimum sphere size, which is 17.3 meters, or let's see that a few times, otherwise known as 55 feet. So that is going to give us our sphere. Now, if we're following along with IEEE 998's methodologies, we can do a lot of hand calculations and mathematical equations in order to determine, based off of the height of this mast, we can determine at what point the sphere will make contact with that. And fortunately for us, this is going to create multiple right triangles, and we get to use one of our favorite equations, the Pythagorean theorem, in order to calculate. We know this distance from the origin of our sphere to maybe the top of our mast, and that can tell us, based off the top of the mast, the height that our sphere will make contact with that. And then we have our S minus A being either the mast height or the base conductor's height, and we can just create multiple right triangles in order to calculate our striking distance, in order to calculate how far away we can put these masts in order to prevent the sphere from rolling through this and making contact with our base conductors of our substation. Now, this will end up with a lot of math calculations, and it walks through multiple different methodologies for that. If you have a relatively standardized design, this may be an applicable approach. More often what we'll see, though, engineers doing or designers doing is we're going to take that concept and then just put it into some sort of software or CAD tool in order to help us evaluate that. One of the simplest ways, if we have, let's say, MicroStation, for instance, I already have a very simple illustration here. So I will rotate my view. You can see this is just a wireframe of a simple building. And if I rotate from the right, I have a sphere size. And this one is 150 feet across, or 150 feet as the radius. So it's the 45 meter across NFPA value. And what I can do with this is I'm just going to copy this value. And I can look to see, as I move my sphere across my system, you can see if it's making contact with the structure, it wouldn't do that because I actually have air terminals that will prevent that. And the air terminals are illustrated in orange here. Now I have my view from the right. We'll have to replicate this as we look from the front view of this system and roll the sphere over this way. This is one methodology that is relatively common in the industry, but there's a little bit of a concern, is that we're looking at a sphere that's a three-dimensional object. We're trying to protect a structure that is a three-dimensional object. And if we're evaluating it as a two-dimensional views, we can have holes in our analysis. So what I mean by that, we can really illustrate if we go through a case example. So we can go to more complex software. So we have the SHIELD module here that we can use to do this. And I'm just going to import that CAD file. So I'm going to navigate to the structure that I want to import. I just need to call out the scale of this structure, and then I will pull in the lightning protection system. I'll note that as a shielding system. Then I will pull in the structure that we want to try to protect. Apply this. And then with my scale correctly here, I can import this, and then we're going to see an illustration of the lightning protection, or the structure with its lightning protection system on it, as we see here. And now we have a 3D environment that we can actually analyze this. And I want to specify the striking distance of 150 feet. and we'll make sure that we're referencing the shielding before we go into debug and compute this. And as this is analyzing, we'll see a little load bar in the bottom right. But essentially, this is rolling the sphere three-dimensionally across our system. And when we look at this system, what you may have determined to be a compliant system from a 2D perspective is pretty easily highlighted to show as not protected from a three-dimensional perspective. Because if we look here, we can see this sphere actually rolls over the top of the structure, and then we have a little gap that we may have missed in their terminal. And this would highlight for us as the designers, as the engineers, that we didn't properly apply NFPA 780, for instance, and we need to go back and mitigate that, which is simple to do. You just go back in and we'll put in some more shielding here. We'll call this my LPS. And I'm going to rotate my view so I can see this more easily. And we will need to reanalyze this, but we'll just put in a couple air terminals in order to protect this. I do want to make sure this is described as shielding, so it works as that. And I'm going to put in another air terminal at this edge because we did see some issues there as well as on this point right here. So now we have more air terminals that we've added based off of our calculations, and we'll just rerun that analysis so that we can get to a point where we're saying this site is proven to have a protected zone so that any direct strokes will not directly hit our structure. And what we'll do is provide a view of this. So now we can see this is protected zone. We can do kind of a top-down view of this system. Take a snap of that. And do the same type of illustrations that we would with the 2D perspective, but have a little more confidence that this is actually protected. We'll do the same thing on the right side. And we can show a little bit of the interior of our structure so that the clients or our leadership can see that we've actually, as an engineer or designer, have protected this system. And of course, we need to create some sort of report to illustrate that. So here would be just the quick, simple, we have a shielding system and a lightning protection system, and our striking distance is following the NFPA 780 with a 150-meter sphere or striking distance, and our protected zones as illustrated here. Now, this is one approach for that, or a couple different software for doing this. You may see like an open substation, there's other lightning protection system approach or analysis. But we do want to make sure that if you're applying the rolling sphere that you're aware of the fundamental hazards of using a two-dimensional approach for evaluating a three-dimensional problem. And also highlight that it can be really advantageous to prove to yourself that you've applied NFPA 780 properly. Another application is, if you have a more complex structure, so we see this illustrated here, or I've actually done one where it's a building in Revit or open buildings here. We can see this analysis would show, if we look at a more complex system, when we look at the results of this, we're really concerned about the upper floor and making sure that we've provided air terminals on all those spots. As a designer, we may have missed a spot, meaning we may have not included air terminals on a secondary level or a lower level that didn't catch our attention because we were focused on the roof line, for instance. So this is just little ways that we can help improve our design and analysis approach to help keep our infrastructure protected from the hazards of lightning. Now, getting back to the presentation here, When we talk about lightning protection systems, really we were just giving like a basic overview of some of the components and approaches for this. There is a much greater depth of knowledge that you can look into for understanding how our various approaches for lightning analysis, lightning shielding, lightning risk. How you approach these could be a bonded or isolated system. So you may have a lightning protection system that is bonded to all the other metallic components of your structure, or you may have one that's isolated. This would be really important to have in areas where you have combustibles or explosives. You would want to have an isolated system to make sure that you maintain separation. There's no sparks in an area that could cause a significantly worse hazard. With that, we need to be cognizant that there is a separation distance to be aware of. So as you're installing your down leads or your air terminals, if it's running right next to a venting system, you may be able to have a side flash occur because you are not maintaining sufficient separation for that. In those instances, you may, as a designer, need to change the path of that down lead or the air terminal. You may need to create some bonding to that. Bonding could be a positive effect or it could be a negative effect because you may, by bonding, expose your structure to a portion of that lightning current. So it's something that as an engineer or a designer, you need to be cognizant of what may be best for protecting a specific type of facility. Other things are surge protection. So if you have your lightning protection system developed, it's going to try and discharge into the earth and through that grounding system. You may have opportunities for induced voltages on your power system, and you may need to mitigate that with some surge protection devices, especially for sensitive electronics. That's a good way to help provide an external lightning protection as well as protect the electronics of your system. And maintenance techniques or maintenance practices. Many times we need to be cognizant that this is generally a passive system until it's required to operate. So the lightning storm or thunderstorm, as it's coming in, you will see some current being developed on your air terminals, on your ground grid, and all of those effects can lead to some damages. You will most likely want to have some sort of maintenance steps every 3 to 5 years at a minimum. Obviously, it's good to provide some sort of inspection of the air terminals, the down leads, the connections, and the earth, the grounding grid after storms to verify that if there was a strike that you are able to identify any damage and provide a replacement for that equipment. Also, damaging events. This can be something that's like a high wind storm, corrosion, or simply theft. If that's something that comes up in your facilities, you need to be cognizant to do sufficient maintenance and inspections to verify that you have the protection installed, even when others may be walking away with some portions of that. Now, in conclusion, I really want to highlight that when we talk about lightning analysis as an engineering or designer, we're really talking about a few different things under the same umbrella. This can be a risk assessment, or it could be a shielding design to determine the protected zones versus unprotected zones. It may be a detailed analysis or a lightning transient analysis to determine how that stroke current is going to propagate through our facility and our lightning protection system. We want to make sure that you know that there are multiple methods in order to evaluate the protected zones and verify that your lightning protection design is actually providing that protection from your structure or your facility. At this point, I think it's a good time to open up for any questions that you may have as we walk through this webinar. Again, this is really meant to be an introductory webinar. I think it's good for much of the audience here that were new to the subject and learning this. If you have any questions, do feel free to place that into the GoToWebinar questions chat box, and that'll give us a chance to answer those. I'm going to go ahead and look over to the questions. One question that came up is if the slide deck will be provided or if this session is being recorded. Yes, this is a session that we are recording, and we will be putting this onto our website. I believe attendees and those that have registered will receive a notification once that recording is available. So you'll be able to refer to this later. Another question is, do we have any materials related to the risk analysis in more detail? For this webinar, we don't have them at this moment, but just wanted to present the general concepts. If you're looking at NFPA 780, I can't recall the exact annex, same with IEEE 998. Both of those have detailed guidance on what factors you may consider in your risk assessment and the probability of a lightning event occurring and the damage that would incur for that. And often what these will come up with is a risk or a cost of damage per year, and that you can use that in order to justify the expense of a lightning protection system. And I didn't mention this in the webinar previously, but it can be a significant benefit to have a lightning protection system just for reducing your insurance costs as well. So that can be something that's factored into your risk assessment, is that you can have a reduction in insurance rates as well. Another question is, when should one use the fixed angle method versus the rolling sphere methodology? It really depends on the engineer and the application. From my perspective, you'll see the fixed angle method used very frequently in transmission line applications because there's a relatively fixed space or height difference between your phase conductors that you're trying to protect and the shield wire that you're using to protect those phase conductors. So that makes it a relatively simple application to use that fixed angle method. Some structures are more easily evaluated with that simplified fixed angle approach. Typically though, if you have the software, if you had a CAD package, you can have easy access to do a more robust rolling sphere methodology. And usually buildings, like if you're designing something in open buildings or Revit, that can be a more critical building that you would want to design and evaluate more robustly with the rolling sphere methodology. One question is, are there any documents or drawings that EasyPower might have on lightning protection is typically connected to a ground grid at a plant? I'll say yes and no. So if you download XGSLab, if you're a user of XGSLab, then there are multiple tutorial documents, and there's a couple generation facilities in the tutorial documents. So that provides just a brief example of one application of that, but I wouldn't use that as the guide for how to design these systems. There's a few vendors that have really good documentation. Dane is one that has I think it's a 500-page manual on the concepts and design application for lightning protection systems and how to evaluate them. So there's many resources online that you might be able to look into, as well as, of course, the standard documents. They're meant to provide guidance for how engineers and designers should approach protecting our critical infrastructure. Another question is, if maintenance is recommended after a storm, how do we make a judgment call if we need maintenance, or how do we evaluate the intensity of that storm that may need some maintenance or visual inspection? There's a couple different ways I can think of this. One is obviously categories of tornadoes or high winds that can launch material in the air, and then that can make contact with your air terminals and your down leads and all of your protective equipment. That could be one example of a case where you may want to look into a maintenance procedure for reevaluating your LPS. Another is if you are getting lightning measurement data. So there are terminals throughout the US that is actually measuring the stroke current magnitude, the exact time of the stroke, and then the general, as best they can, try to locate where that may have occurred. If you're receiving that information or purchasing that information, you may be able to look to see if one of those strokes was within proximity of your equipment, whether it's a substation or a power plant, and that may kick off a evaluation. And of course, if you had an outage during a thunderstorm, that would be a very good case to look into some sort of maintenance procedures and inspection. So another question is what can be applied as a mobile structure, like a container? And there, again, I would point towards NFPA does have guidance for things like ships as well. IEC does as well have guidance for what we'll call mobile systems. If you're just moving a mobile system around, you have, and I'm not going to discuss the ship application right now, but let's say you're moving a container from one location to another, you need to have all three components of that lightning protection system installed. So that'll be the air terminal, the down lead, and the ground grid in order to disperse that energy. It should be noted as well that there are some structures that would be self-protecting because of the thickness of the material of it. It can withstand a significant amount of current that it can withstand the thermal limits as well as the physical limitations of that stroke current. Another question is, does this software offer comparison of the lightning protection performance with surface corrosion conductors to ideal conditions? The corrosion aspect and more detailed analyses, so that I guess we'll kind of want to break this up in a couple of different ways, but when I think about your analysis in more detail, we're really looking at your grounding system performance and making sure as your down leads or your terminals are providing that path to ground that they're not going to induce enough current on some other object or create a significant enough voltage difference that you'll have some side flash. So for those, you'll typically have very high voltage values or magnitudes, and that can often go through any sort of corrosion that may have formed or thin film of corrosion. So that corrosion typically doesn't have the dielectric strength in order to prevent that. I do want to highlight though that if you have a significant corrosion risk, that can play into your maintenance issues because your connection that you thought was robust will pull off in the event as it's happening. And so that can lead to unintended damages elsewhere. Another question is there a way to model a metal railing as a strike terminal in the software? And is that allowed per NFPA 780? Yes, so NFPA 780 does allow for you to take advantage of your system design. If you are, again, having all three components of that system, a railing can serve as a air terminal, and you need to have downlead from it or some sort of continuity to your ground grid in order to disperse that energy. And that's something that's mentioned in NFPA 780. And you can, in XGSLab software, it's a pretty flexible tool. So what we will do is be able to import whatever your structure may be. We are going to import and this import process, I kind of showed it in the simplified view, but we can pull in several of the layers from whatever CAD package you're using in order to do this design. And then we just want to make sure that we denote for the software what parts of our system are the structure that we want to protect, whether that is a building or our phase conductors of a substation, whatever it may be. We just need to note that as a structure type, and then we have to know what things are a lightning protection element. And I didn't show this in this calculation either, but if we go to the XGSLab analysis again, we just use this striking distance of 150 feet. The calculation can be determined in this software, so you can calculate the stroke current, and it kind of gives you a nice little guide of all the parameters that you would need to enter in order to calculate that surge impedance and then that corresponding stroke current, and then of course our final goal of that sphere size. Another question is, can we look at installing a catenary system? So this is pretty common, especially for explosive areas. We would install a catenary system. So if I go to let's do my simplified building here. That way it can run relatively easily. Let's say I want to put a catenary wire going across some portion of this building. Let me place this in here. I'm going to make sure I know the height of this facility before I design this. So the conductor is, the top edge of this building is 50 feet in the air. So let's say we're just going to put our counterpoise, our air terminal, 70 feet in the air. And so I want to make sure this is designated as an LPS, and I'll call this my catenary. So I can put in this conductor, and right now, just a nice straight line. What I want to do is actually make this something that's curved, and so I want to know the approximate length of this conductor is 108 feet. So this catenary tool is a way for me in my software to add that later on. If you design that catenary in your CAD package, obviously XGSLab would import that and analyze that. So we have our starting point is 0, our elevation is 70 feet. Let's say at 50 feet, we drop down to 65 feet in elevation. And then we go to the end location, which is 100 feet. And then we have this ZE, where we're back up to 70 feet, where our maths are supporting that catenary wire. And this will calculate a parameter, a catenary constant. And then this is something that I can take into my model, and then I'll select this conductor, my shield wire. In my layout, we have the catenary parameter. And once I apply that, then we can see that sat characteristic. And with this, if you're in an area that you want to avoid any side flash or side strike, you will want to make sure the elevation of this is sufficient between the structure you're protecting and the location of that catenary curve. And I'm going to run this as I look into the next question, so we'll be able to take a look at the results from that. Another question is just related to the video. So I do want to clarify the video, we're recording this session and we will have this on our website. So you will be able to see a recording of this presentation on our website. Anyone that's registered or attended this webinar will be able to see that after the fact. I just want to illustrate here. Now you can see that catenary curve is, that catenary shield wire is providing some protection for our structure down below. And I do want to highlight, as we are at the top of the hour, I'm sure people will need to drop off. If you have any questions, feel free to reach out to me at dave.lewis@bentley.com. You can reach us at EasyPower or XGSLab support. Especially if you're a user, feel free to ask any questions that may come up. But very much appreciate everybody jumping on the webinar. If you have other questions, I will stay on for another couple minutes here to answer those as they're coming up. And if I didn't get your question here, if I accidentally missed it, I will make sure to answer that. If you can, do provide comments on the exit survey. Really appreciate any information as you attend to this webinar, things that we could do better or things that you'd like us to explore in more detail. Again, thank you everyone for attending this webinar today. I think this might be our final question. So are we able to link this software? So the XGSLab software is what we're using in the analysis here for the rolling sphere. So are we able to link the XGSLab SHIELD software with others like Revit to import structures? Absolutely. So here, just to show you, this is the Revit file that I started with for my analysis. And so I'm just exporting this out to a readable format for XGSLab, which is just really a DWG TXF file from them. Similar concept applies when you're using a MicroStation or open buildings, you'll be able to export from whatever CAD package you're using into a readable format with XGSLab in order to do these types of analyses relatively efficiently. And here, just want to highlight again, when you're using XGSLab, I can import the layers or the levels that I want to bring in. It illustrates the building, as you can see here, and then we're going to evaluate the lightning protection system and how the terminals are hopefully preventing any lightning strike from hitting our structure directly. Again, thank you everyone for attending this. I'm going to go ahead and close our webinar, and do please enter your comments for the end survey. We really appreciate everybody calling in today.